coming in. So I'm taking the mask off. Just let's see, what do I do? I must be suffering from brain fog. I've forgotten how to use this thing. It's I guess you stick it in here and okay, so I'm going through at a pretty slow pace. That article by Langlands on the Bachner issue on problems in automorphic forms. And I mentioned there's we did three applications. One was the functional equation. The real, I guess, purpose of those notes was to introduce the principle of functoriality, but it wasn't called that at the time. And then there were four applications. One was analytic continuation and functional equation of all of the L functions that were introduced. Two was non-abelian class field theory. Three was the Ramanujan conjecture. And the fourth application was one sentence at the end of the article. And it was on, so I'm going to say a little bit about that. So I'm writing these applications as 1, 2, 3, 4, and I'm putting a little f to indicate that they are four applications flagged by Langlands in that article of functoriality. Now, I'm not in a position to describe how the generalized Sato-Tate conjecture would follow from functoriality. I didn't think about that. It was proved by Taylor, Harris, and others. Taylor and various collaborators not too long ago, in which he used very clever arguments to bypass the principle of functoriality. And he comments, I mean, I didn't really go through it, but I think it's like the Ramanujan conjecture. If you assume functoriality, I think that it follows rather more easily. But Taylor and his collaborators got around that by using other things, base change, I think, for GLN and various other things to prove it. So I'm going to talk a little bit about I'm going to call it the generalized, I won't really say much about the general, I'll sort of set it up, but the generalized Sato-Tate conjecture. And it's a very natural thing to mention by Langlands at this stage of the argument. So it's a conjecture by Sato-Tate, and it was posed as a question by Langlands in greater generality. He didn't really set it up, but question for hospital. Automorphic representations by. And so what's the setting? I mean, we can sort of imagine what the general problem might be. So the setting, why don't I just take the same setting that we had for talking about Ramanujan's conjecture. So G over Q is a split reductive group over Q. And we'll use the same notation that we had before. We've got the dual group, we've got a Borel subgroup, we fixed those things, and we've got a maximal torus T in the Borel subgroup. All right, so the question is, we've got a cuspidal automorphic representation. Of GA. And the fundamental part of that is what Langlands set up in the earlier part of the article, namely the family of semi-simple conjugacy classes in T hat. So, or we could say, I guess we should really say family of semi-simple conjugacy classes in this complex group. So these are, pi gives you family C sub p for almost all primes. Some primes would ramify, so remember we throw away. There's further questions, as we know, that can be posed for the ramified pieces and the Archimedean piece, but the sort of really basic fundamental information is these families of conjugacy class, semi-simple conjugacy classes attached to prime numbers. So there's a family of semi-simple conjugacy classes. In G hat. Now this is a question that is to be posed after you've done Ramanujan's conjecture. So Langlands gave the argument for Ramanujan's conjecture, and so we assume at this point so we can assume Ramanujan for pi. Otherwise, you can't even pose the question in a reasonable way. And then remember what Ramanujan conjecture says is that each of these conjugacy classes in this complex group intersect a maximal compact subgroup. So then the classes CP each one way to say it, Ramanujan's conjecture is that these classes, these are conjugacy classes in a complex group, but they each intersect a maximal compact subgroup of that complex group. And if they're semi-simple conjugacy classes, they not only intersect the maximal compact subgroup, but they intersect a maximal torus in that compact subgroup. So these, Ramanujan's conjecture then would imply that each of the classes CP intersect the compact part let me write it as U hat of the maximal compact torus T hat in the Borel subgroup. So what we've got is a compact, an old-fashioned compact torus, T hat, not an algebraic torus, but an actual compact torus. And we have a bunch of conjugacy classes in the compact group K, which intersect this. So, so C, so C can be regarded as a family. Well, I think I'm repeating myself here, but so C can be regarded as a family, CP. Okay, so these CPs, they intersect. They're semi-simple conjugacy classes in, let's say, a reductive compact torus. So that means they intersect, so they're semi-simple conjugacy classes in a compact group, K hat. They therefore intersect maximal torus in that compact group. And what does that, excuse me, what does that mean they are, they're intersections with a compact torus? What does it mean? It means they're an orbit, each one of them is an orbit of the Weyl group. So, so each of which CP is represented as an orbit of the Weyl group, W hat, in the compact torus. T hat in K hat. And so here's the problem. You've got a bunch of these conjugacy classes in this torus, parameterized by prime numbers, infinitely many of them. So here's the problem. What's the distribution of points? So this is you've got infinitely many points in a compact torus. So they're scattered all over the compact torus. What's their distribution? Of points. So what do we got? We've got the set of points CP attached to this cuspidal automorphic representation pi that satisfies Ramanujan's conjecture. And this would be P. We're throwing away finitely many of them. That doesn't affect the distribution of an infinite set. And what we would do is we would take the set of these things in which P is less than or equal to X. And so you're going to get finitely many points in the torus, and then you're going to want to look at what happens when X goes to infinity. How are these things distributed in this compact torus? All right. So let's, I guess, finish the sentence. What's the distribution of these points in U hat as this X is a positive integer, as X goes to infinity? All right. It's going to depend on pi. So this clearly wow, why is that? I mean, there's an obvious example that would be the other extreme that you're within what you're thinking of for sort of a generic cuspidal automorphic representation. If pi is a functorial image, remember, functorial images go from groups G prime to G, in which the dual group of G prime is mapped into the dual group of G. So it's a functorial image from, and suppose I were to take G prime to be the identity element. And then we've talked about this. This is a very important case, as we've talked about. So the functorial image G prime has only one representation, pi prime being the trivial one-dimensional representation. But that's still very interesting to G. Functorial from G prime to G, given by a homomorphism rho prime. Okay, so this is going to be a homomorphism from, remember, in general, GL, the L group, or G prime L, even if G is the trivial one-dimensional group, G prime L is going to be a Galois group, a large Galois group, as large as you want to make it. And so it will be the functorial image of a representation pi from G prime given by homomorphism rho prime, the Galois group of some large Galois extension to G hat. Well, what is C going to be? C is supposed to be the image of it, the functorial image. Well, C it's a bunch of conjugacy classes that are images of the Frobenius conjugacy classes in this finite group under rho prime. So whatever it is, it's extremely interesting, but it's only a finite set of points. This is what we were sort of thinking of as what we know sort of at all. This is what we found was in fact the long sought non-abelian class field theory that would be attached to the principle of functoriality. But in any case, what it is, it's a finite set of points, or rather Weyl orbits, in U hat, this compact torus. All right, now we're talking the traditional Sato-Tate conjecture doesn't apply to this. This is a separate question, what's happening here, and it's of course related to questions in distribution. These things have been studied, distributions of Frobenius conjugacy classes and Galois groups. But what we're really talking about here is the other extreme. We want to, the traditional Sato-Tate conjecture applies to representation pi. It actually applies to SL2, the group SL2. But in general, if we're trying to sort of think of what we'd be looking for, we would want a cuspidal automorphic representation that is the functorial image of nothing smaller, sort of a primitive automorphic representation. So let's make, we're assuming functoriality. So the further assumption that we're going to make on pi in order to try to set up this distribution question, we're going to assume to remove, so it's clear that there's going to be a bunch of different kinds of distributions. The most extreme in one direction is this one here, coming from a representation of the Galois group. Let's remove all of these things. Suppose, so to remove this, how should I say, this is a distraction. We won't worry about these smaller automorphic representations. Suppose that I'm going to say that pi is primitive. In the sense that it's not a functorial image of anything. Is not a proper image. I'll put it, let me write it, let me say it this way. It's not a proper image under functoriality. From any smaller group. So from any group, or from any, it's more than a group that you need to talk about functoriality. It would be a triplet, G prime, pi prime, and rho prime. So under a proper image, so in other words, i.e., you've got G prime and pi prime. This is what we want to rule out, what the kind of thing that I'm writing down here. G prime pi prime gives us a family of conjugacy classes in the dual group of G prime, the L group of G prime. Rho prime maps this to a automorphic representation pi of G, and we've got rho prime over here too. And for an automorphic representation of G, we have C. So C stands, remember, this is a family of semi-simple conjugacy classes. This is a family of semi-simple conjugacy classes, CP. And rho prime maps C prime to C, just takes their image from one dual group to the other. I do not want to include anything from this situation with proper meaning, in which I'm that the image rho prime. I mean, there are cases of functoriality where you have something very closely related to G. It's easy to see stuff that's happening there. But I do not want to include any of these things that rho prime G hat prime is not equal to G hat. I'll throw all of those away. This notion of thinking about the proper, thinking about the primitive automorphic representations of G is also, it's going to come up a little bit later. I do hope I get to this, but it comes up as the essential part of the conjectural description of the automorphic Galois group, and also from that the motivic Galois group. It comes from, it's a construction, conjectural construction, coming from these primitive representations as you let the groups G vary. So throw away all the extraneous ones. So that's what we're going to consider for asking ourselves the question about the Sato-Tate conjecture. All right, so we throw away all these things. We assume G, we assume pi is not any proper functorial image. And so what might we expect? All right, the initial expectation. Okay, so we've got these classes. CP, family of classes, CP pi, for one of these primitive representations, should be uniformly distributed. in the torus U hat. Okay, we got a torus, SL2. Let's say the torus is like from 0 to 2 pi. And so these things run throughout that torus. And we're going to narrow ourselves down to that situation presently. They should be uniformly distributed in that torus. Well, they're not. It's not quite true. This is what one might expect.
So this is the real torus.
This is the this is the compact torus.
No, I mean,
Yeah, just the old-fashioned torus.
the old-fashioned.
The old-fashioned kind of torus, product of intervals 0 to 2 pi. A bunch of circles, product of circles.
Not T hat kind of torus.
Not that T, no, it's U hat. It's U hat, which is in the compact group. So, well, you'd think they ought to be distributed uniformly in that. It's not quite true. It's close. Well, not quite. And when you first see the Sato-Tate conjecture, it's a bit puzzling because of this question. So why is that? Why is it not quite true? Well, the real question, the density of conjugacy classes, because we've got Ramanujan's conjecture, we can work in the maximal compact subgroup K hat. So we're allowed to do that, and the maximal torus in that compact subgroup. But the density of conjugacy classes in K hat is slightly different. Okay, you got two things. You've got semi-simple conjugacy classes in a maximal compact subgroup, like SUN, say, and you've got, they all intersect the maximal torus. So if you're talking about SUN, you're talking about the diagonal matrices in SUN, and you can talk about the density in that. But the density of conjugacy classes in K hat is slightly different from the density of W hat orbits in T hat. I mean, why should that be true? Well, there's a very natural reason why it's true. Well, what should be true conjecturally is that, how should I say this? You've got conjugacy classes in a maximal compact subgroup, like UN, compact unitary group. What should be true is that if you take an open, let's say an opened subset, if H hat is an open, K hat invariant subset of the compact group k hat. Okay, so we've got all these conjugacy classes CP, and we're regarding them as conjugacy classes at this moment in this maximal compact subgroup. I take an open subset of this maximal compact subgroup, which is itself invariant under conjugation. And so then I can ask, what's the distribution of these things? What's the distribution of these conjugacy classes that map into this open compact subgroup? And so the density of conjugacy classes in this, of classes CP in H, some of these conjugacy classes will meet H and some of them won't. But if they meet H, then the whole conjugacy class is going to have to be in H. That's what I'm assuming. I'm assuming H is an invariant subspace under conjugation. And what should they be? It should equal the volume of H. Of H hat. H hat's a subset of this compact group, and we've got a measure on this compact subgroup. We've got the Haar measure. So the volume of H, this would be with respect to the normalized Haar measure. On k hat, i.e. Volume of k hat equals 1. The Haar measure, which assigns volume 1 to k hat. All right. So in other words, we could write it quantitatively as follows. The limit as n goes to infinity of, let's say, the set of CP we'll throw away S, that doesn't matter for this question, and such that CP is in H hat. Okay, but the important thing is, let's say P is less than or equal to a large integer n. Okay, so, and I want to take the number for any given n. I want to take the number of primes such that CP, now it depends on pi, CP equals CP of pi. I want to take the number of conjugacy classes which lie in H hat, and I want to divide it by the number of conjugacy classes P naught in S, with no restrictions except that P is less than or equal to n. So the limit as n goes to infinity of a set of conjugacy classes as P is less than or equal to 1 to n, which lie in H hat, divided by the set of all conjugacy classes with P less than or equal to n. And so that should be equal to the volume of H hat. This would be for any open subset. That's what it would mean to be uniformly distributed, like a little invariant compact, an invariant neighborhood, small invariant neighborhood, open subset of the group k hat. And so the point is, what's relevant to this is that H hat has all kinds of freedom. It can be just anything. The only condition is that it's, well, let's say open and invariant. And then this should be equal to the volume of H. That is not quite the same as asking the same question about conjugacy classes in U hat, regarded as Weyl orbits of elements in U hat. And why, how would we set that? Why would we see that it's a little bit different? So to see this, to see what this means in terms of conjugacy classes of Weyl orbits in U hat, we have to, well, there's a natural thing. Anybody want to take a guess as to what makes the two a little bit different? Well, you've got a decomposition. We're talking about the Haar measure, the volume on K, but the restriction of that volume to U hat has to, it's a, excuse me, it undergoes a change of variables formula if you restrict the Haar measure on K hat to the natural Haar measure on this maximal torus. To see what this means in terms of Weyl orbits in U hat, we have only to recall the Weyl integration formula. Which says that conjugacy, if you wanted to identify conjugacy classes in K hat with their intersections with U hat, you have to we have to realize that they get stretched if you go from one to the other. They get stretched by this Weyl integration formula, namely, if f is, let's say, a continuous function on K hat, then we've got the volume on K, so the integral over K hat of f of x dx. This would be with respect to the Haar measure on K hat with, let's say, volume 1. And how does that play out when you look at the corresponding integral over the maximal torus? Well, everything up to a set of measure 0, everything in K hat is conjugate to something in the maximal torus. So there's going to be a relation, but it's just a little bit different than we might have initially guessed. The integral, might as well, we could even assume that f is an invariant function, but the integral over K of f of x dx is a little bit different from the integral, the product of integrals, the integral over K hat modulo U hat, and then the integral over U hat. It is the, so it's a double integral. It's the integral, first of all, you divide out by the number of elements in the Weyl group. You then take the integral over U hat of, and that, this thing here is a Jacobian determinant. It's just, it's a formula that everybody, we all teach calculus, second year calculus students. You have a change of variables in multiple integrals. You have to take into consideration the Jacobian matrix and its determinant. And so that's what's happening here. It's the integral over U hat, the double integral, the integral over U hat, K hat, modulo U hat of f of x to the minus 1 U of x dx du. And that's not difficult at all to prove in the general scheme of things when you're talking about Lie groups and change of variables formulas in Lie groups, semi-simple Lie groups. Okay, so I have to say what these things are. Well, we've already said what W hat is. That's the Weyl group. That's the normalizer in K hat of U hat, finite group. But the critical thing here is so the critical thing is, oh, we have this big brush there. I should be using that make it cleaner. Oh no, you got to wash it. No, I won't do that. So, so the main thing is you have d of u is a Jacobian determinant, and it's the determinant of the linear transformation on the Lie algebra of the on the quotient of the Lie algebras of k hat and u hat. So it's the determinant of a linear transformation 1 minus add u. U is an element in u hat. I take the adjoint representation of u hat on the Lie algebra of k hat modulo the Lie algebra of u hat, and then I take 1 minus this, and I take its determinant. So this is called, this thing comes up all of the time, as many of you will know. This comes up all the time when you study Lie groups and integrals on Lie groups. This is known as the Weil discriminant. It's very closely related, actually. Discriminant. When you're dealing with the general linear group or the unitary group, it's very closely related to actually the discriminant of the characteristic polynomial. But in general, in this situation, it's known as the Weil discriminant. So this gives the density of things in u hat in terms of du. So you have this things that weights the density when you try to count collection of things in of conjugacy classes, infinite collection of conjugacy classes in k hat. You try to compare that with their the density of their intersections with u hat. You don't quite get quite the same thing. You have to weight the latter by this thing. So with that said, then we will look at, this is sort of crazy, but I have a concert tonight. I'm going to wander through the snow. I don't, but in any case, so I'll quit at 6 if that's okay. But let's just start. So the example, nobody's looked at this question because we really don't know functoriality. So it was considered quite a breakthrough for the special case that that G is equal to, or that K, let's say, well, a special case that G is equal to SL2 and K is just the torus. So the original Sato-Tate conjecture that was recently proved by, well, not so recently, but not too long ago, proved by Closel, Harris, Taylor. It was a large collaboration. plus others. I don't have the names of all of the people on the written down. And this applies to what we've been saying up here. It applies to G equals SL2 pi a cuspidal automorphic representation of GA SL2A. But we have to make sure that it's primitive in the sense we've set up here. So it can't come from a representation of a Galois group. And it also cannot, well, I actually set it up for an elliptic curve, which is translates into this. The original thing was actually for an elliptic curve. And the critical point, even for the automorphic representation and the elliptic curve, you cannot, it has to be primitive. So that means it's not of CM type. That's the condition that Sato and Tate put on the elliptic curve, because the answer would be different in that case. It would be simpler and not as interesting, i.e., so if I could either think of this in terms of automorphic representations or of elliptic curves. The two we know are the same, thanks to the proof of Shimura Tanyama Bay. We're talking about something over Q, and all of this was G is over Q. So not the functorial image. This is the only way it could not be primitive, not the functorial image of an abelian algebraic group. I mean, this is still very interesting, but CM type means, as you no doubt know, of an abelian algebraic group G prime, the restriction of scalars from E to Q of GL1 for an extension, for a quadratic extension. For a quadratic extension, E over Q. Okay, so there you can. This is an abelian algebraic group. There's a natural homomorphism from its L group into the L group of SL2, and we don't want to include that. It's going to give us a different answer. Okay, so we'll leave it here. It's 6 o'clock. We'll leave it here, and I'll just recall. I mean, we'll go through. We'll just look at. Some of you may have already done this, but depending on how much you've sort of your background is, but we'll just go through this and we'll see the difference between what happens for SL2 and what happens for its maximal compact. What happens for SL2, that's SU2, and what happens for its maximal torus.